Hello, good morning all of you. Hope you are ready with your notebooks and pens and for the session. Previous class began with the electrostatics, the first unit, the charges and the Coulombic force. In that, we understood what is meant by electric charge and we started discussing about the properties, the characteristics of charge. And in that journey, we said charges are of two types such that like charges repel and unlike charges attract. This is one property. Second property was quantization of charge. We have said A part and B part of the statements and that popular Q charge is equal to small n times E. Remember what was that n? An integer. E for electronic charge, the fundamental charge. Now today, as a part of this quantization, why this quantization? Let us put a question and we'll get an answer according to our modern electronic theory. Now, in the beginning of the 20th century, it is established that the smallest entity of the matter is atom, and the atom is again made up of some charged particles. Now let us see what are those important 5 to 6 points regarding modern electronic theory. Now, atom is made up of, yes, negatively charged electrons. Next, positively charged protons. And also chargeless particles, neutral, and hence the name given as the neutrons, chargeless neutrons. So this is what is atom is made up of. Electrons with negative charge, protons with positive charge, and the neutrons, the chargeless particles, such that though atom is made up of these charges, atom is electrically neutral. Why? Because the number or the magnitude of the negative charge, the total magnitude of the negative charge due to electrons is the same as the total positive charge due to protons. Therefore, the total positive and total negative charges equal in magnitude, net charge is always 0 on in the case of atom. Net charge I am telling you, atom is made up of charges such that net charge is 0. So this is our first basis of electronic theory. Now comes the next thing. Where does these protons reside? We know that nuclear model of atom by Rutherford, which says that all the positive charge is inside this nucleus with very, very strong forces between them. Whereas electrons will be revolving outside the nucleus in different circular orbits. High school knowledge and also your first PU chemistry also told about the structure of the atom. Electrons now revolving around the nucleus, and they are bound to the nucleus, and that will be a kind of weaker force as compared to forces between the protons, which is very, very strong force. Electron binding with the nucleus is a weaker force. Therefore, now what is meant by charging a body? Now let me write charging, otherwise called as electrification. Look at this term, charging or electrification. Atom is now having charged particles, but the interesting thing is that atom is electrically neutral. Neutral means net charge is 0. Again, net charge means, yes, since it has positive charges and negative charges, we have to consider the net charge, and that is always 0 for an atom. Therefore, according to modern electronic theory, modern electronic theory, the total positive charge in the atom, which I am calling as Q plus, is equal to Q minus, because charge of the electron negative, charge of the proton positive, but the magnitude is same, such that Q plus is equal to Q minus. This means number of electrons is equal to number of protons. So whatever charge is there by the electron, it is balanced by the protons. Atom electrically neutral. Now, we come to the point of charging or electrification. What do we mean by the process of charging or electrification? According to modern electronic theory, now we introduce this term. Remember, an important thing, 1 mark, 2 marks, you will all see those questions. Now, our term is, yes, electrification. Otherwise called, what is electrification? Or what is meant by charging? Both are one and the same. The process of charging. Now, we can disturb electrical neutrality of the atom. Disturbing electrical neutrality can be two ways. How? By adding positive charge or removing positive charge from the nucleus. It is one way, right? What is that? I repeat my sentence. Disturbing the this electric neutrality of atom can be two ways. How? By changing the number of protons in the nucleus. You decrease the number by removing, or you increase the number by adding protons. This is one way, but this is very difficult. It's a very high energy process, and in normal circumstances it is not possible. It requires very extraordinary conditions that we will understand in our part 2 syllabus also. Therefore, we just don't discuss about that here. The second one is disturbing electric neutrality by changing the number of electrons. So here, electrification, I will term it as, yes, disturbing electric neutrality. Is that okay? Disturbing the electric neutrality, the neutral nature, electric neutral nature by changing, or I will write by either, again two ways, either gain of electrons, by the gain of electrons, or loss of electrons. So now whenever we speak of the charge, it is always the net charge. You should remember, whenever we say whether it is a particle or whether it is a conductor, whenever we say that, it is always we speak about net charge. Now why that charge is arising? Because of the gain of electrons or loss of electrons, such that, see here, gain of electrons. Gain of electrons, what happens? The number of negative charged particles increase. Supposing, let us take the case of oxygen. If I say oxygen, yes, oxygen has, yes, 8 electrons outside the nucleus and 8 protons inside the nucleus. Let us not bother about neutrons because it is charged character. We are keeping aside. Therefore, 8 electrons and 8 protons, such that what is the net charge? Net charge is 0. Now, supposing I said gain of electrons, instead of 8 electrons, supposing it has gain 1 or 2 electrons, then it becomes, suppose it becomes now 10 electrons and 8 protons. What we find is that negative charge is more. By how many units? You will see here by 2 units. Got it? By 2 units, the negative charge is increasing. Remember, we are not now referring to the total positive charge and total negative charge. The expression always gives you net charge. Therefore, now what is observed? Gain of electrons gain of electrons, atom acquires net negative charge. Atom acquires net negative charge. Since it is the gain of electrons, we can now say, we can also add one trivial thing. It is a trivial thing. What is that? Net negative charge whenever atom acquires, since it is because of the gain of electrons, mass of atom increases slightly. Because we know that mass of the electron is very, very small, of the order of 10 power minus 30. 1 kg, unbelievably small, negligibly small. But still, even if we consider that, the mass of the atom will increase. Is it okay? Now, what about the second case? The second case that we are discussing, first one was the gain of electrons. Now let us say what happens due to loss of electrons. Loss of electrons. Now it is your turn. You only write for that. Gain of electrons. Yes, net negative charge we said. Therefore loss of electrons. Atom acquires net positive charge. Atom acquires net positive charge. Here we said mass of atom increases by very slight amount. Here also we say, since it is loss of electrons, mass of atom decreases slightly. Decreases, underline. Positive charge. Loss of electrons, mass decreases. Of course, I am using that adjective slightly. Slightly. Now you see, it can be 1 mark, 2 mark questions for you. If atom becomes positive ion, what happens to its mass? If atom becomes negative ion, what happens to its mass? Your knowledge of chemistry will tell you what do you mean by positive ion and negative ion. Even now also we have mentioned the same. Now what is meant by positive ion? Atom losing electrons. Loss of electrons, it is the case of positive ion. Since it is lost, the mass of positive ion is always slightly less than that of atom. Explanation. Similarly for the negative ion, you will write it as why? What about the mass of negative ion? If it is the case, a question for you, then it is an atom becomes negative ion if it gains electrons. Right? Since it is gain of electrons, mass of the atom slightly increases will be our answer. Right? Now, why quantization now comes? Modern electronic theory says whenever the conductor or a particle is acquiring charge, it is because of either loss of electrons or gain of electrons. So whenever we come across this kind of charging, wherever we get the charging, what happens in the case of charging? Right? Yesterday we have mentioned that example of glass rod or plastic rod rubbed with silk cloth or wool or fur. There we said that this plastic rod or glass rod is acquiring a new character called as charge, we said. So how that is happening in the case of charging, because it is nothing but friction we are creating. When glass rod rubbed with another cloth, we are creating friction. In that process, what is happening? There are now two objects, A and B. If A and B are rubbed together, what happens? One of them, depending upon their character, depending upon their nature, one of them loses electrons such that the other one will gain the electrons. A and B rubbed together, if A is losing electrons, those electrons lost by A will be gained by B, such that A acquires positive charge and B acquires negative charge. So in all the process of charging, what is happening? Exchange of electrons happening between the two systems. That is what we call it as charging. Got it? So what is happening in the case of charging? Exchange of electrons. One losing electrons or the other one gaining electrons. This is what is meant by charging. Therefore now we got the answer for that Ne also. Why? Because N is an integer. Why? Because an atom can lose 2 electrons or can gain 4 electrons. This number 2.5 or 3.9 does not arise, and that is what is quantization. So we have given a very detailed explanation of quantization. Now let us come to few more characteristics of very important characteristics of charge. Remember, you follow each and every statement. After the class also you just write your notes. You will find many 1 mark questions, 2 mark questions to begin with in the characteristics. Now let us proceed with the few more characteristics of charge. Now how this atom looks like, electrons, protons and neutrons. It is the famous Rutherford model which you know from your high school days. Even in first PU you learnt it, right? Now what is atom? See, this is considered to be an atom. All these positively charged protons and chargeless neutrons are present inside this core of the atom, which we call it as nucleus, right? This part is what is nucleus, which has all the positive charge and neutrons. And now what about electrons? Electrons will be revolving around the nucleus in different orbits. This is what is our simple basic knowledge from high school and also from first PU. Now the point is, these protons inside the nucleus are bound with very, very strong forces. Therefore, in normal circumstances, we cannot add protons or remove protons. I repeat my sentence. In the case of protons, the removal of protons to the nucleus or from the nucleus or addition of protons to the nucleus, I said it is not possible. I said it is very, very difficult. It's a very high energy process. So normal circumstances, we cannot disturb the number of protons. What about these electrons? Electrons, this binding with the nucleus is a kind of weaker force. Therefore, we can now disturb the number of electrons in an atom. Disturbing means, yes, decreasing the number of electrons and decreasing the number of protons. Decreasing the number of electrons or adding the number of electrons. Now, two important terminology that we come across. Let us now define them here. Again, important for your 1 mark question, 2 mark question. Now, earlier we said what is meant by charging. It is either loss of electrons or gain of electrons. In such case, when we consider any substance in the form of gaseous state or liquid state or solid state, whenever we consider a substance which is made up of large number of electrons, protons and all, now our discussion is only about electrons. Even in that electrons or even in the case of those electrons, there are 2 types of electrons inside the substance. Again, this is a small knowledge of chemistry. We are not going into the too much of details, but according to chemistry we said that inside the substance there are some electrons which are bound electrons because of the chemical bonding, and there are certain electrons which we call the valence electrons, the loosely bound electrons. Some of the loosely bound electrons, they become free. That is, they will not be under the influence of any of the nucleus. Such electrons are called as free electrons. So when we have a substance, there are 2 types of electrons inside. What are those? Bound electrons and free electrons. Now that loss or gain is possible only with respect to these valence electrons, which we call it as free electron, such that now 2 important definitions. Now materials are classified into 2 or in fact 3 types. conductors, insulators, and one more category, special and interesting category, semiconductors, which is a very big topic for us in second part syllabus. You will learn it in detail. Now, what is meant by conductor? I said materials classified into three types. First one is conductors. That's the next. The second one is insulator. This insulator is otherwise called as dielectric. Di, no space. It's a one single word. Die. D-I-E-L-E-C-T-R-I. See, dielectric, which is a very familiar term that we use. Most of the terms will be using dielectric, not insulator. So both are one and the same. Conductor, insulator. In between we have a category called semiconductor. Semiconductor. For those who are now following the lesson, you should also have a doubt. Semiconductor, same way, is there any possibility for semi-insulator? Right? You have any such doubt? Yes, if you have your doubts, you can call your teacher and discuss with your teacher. Now, what is meant by conductor? Conductor is a substance which high density of free electrons. High density of free electrons. Remember, I have told you bound electrons and free electrons. It is not high density of electrons, it is high density of free electrons. High density. To give you an estimate of that, if it is high, how high it is if you have such doubt. Now, high density, I am telling you, the order of 10 raised 22 electrons per centimeter cube, or even this can be 23 also. Look at this number, 10 raised 22 electrons per centimeter cube. Centimeter cube is a very small volume, and this is what is the number. That is what is the high density. Always remember, I have told you about the units. It is per centimeter cube I have taken. If you want to convert that into meter cube, a centimeter cube converted into meter cube is 10 raised minus 3 get. Therefore, numerator value increases by, so this is becomes 10 raised 28 it becomes, right? 10 raised 28 number of free electrons, not the total number. Free electrons per meter cube it becomes. Such should be the high density, right? Then it is called as conductor. Conductor. Now, what is meant by insulator? Insulator is the material with very low density of free electrons. Now, as compared to 10 raised 23 or 22 per centimeter cube that we have taken, even this 10 raised 11, 10 raised 12 also happens to be very, very small, because it is the order. Remember, 10 raised 10 appears to be big number for us, no doubt. But compared to 10 raised 22, it is as if you are comparing 1 rupee with 100 crores. 1 rupee versus 100 crores, definitely 1 rupee is negligible, or we don't consider that. And that is why, in the case of insulator, though the number may be like very huge, appears to be very huge, but in comparison it's a very small thing. So that is what is insulator, low density of free electrons. Now here comes this middle category, which you will be dealt with in detail in second part of the syllabus. Semiconductor is now the material which is not as high as that of the conductor, not as low as that of insulator, and that is why that category is what is called as semiconductor. So this is how modern theory of electrons will explain the quantization, why quantization, and also the two more definitions. What is meant by conductors? Give examples. What is meant by insulators? Give examples. What is meant by semiconductors? Give examples. Now if I have to give examples for conductors, yes, conductors, all metals are good conductors. All metals are good conductors. Now what are insulators? Insulators, we can give a number of such examples. I would like to say, for example, glass is an insulator, rubber is an insulator, plastics, right? Insulators. Maybe in the modern days, there are some plastics which are conducting properties also, and that is why when we are writing plastics, we should be very careful. Some plastics are insulator, some plastics are, yes, they are conductors as well. Glass, rubber, plastics, mica, all these things. In fact, pure water is also, yes, insulator. Pure water is an insulator. Now comes another point, let us add, and one more here. Semiconductor. Semiconductor example. Here also again, semiconductors, different types. You will of course come to know that. Here I am mentioning pure semiconductor, natural semiconductors which are available in the nature. They are fourth group elements. In the periodic table, you know, fourth group, the carbon group. In that carbon group, yes, silicon, germanium. These are the only two examples that we are mentioning which are naturally occurring semiconductors. Examples are silicon and germanium. This is one example. So, conductor definition, examples. Semiconductor definition, example. Insulator definition, examples. Now the point is that whenever we take the conductor, because of this high density of free electrons, yes, it conducts the flow of charges. It allows the flow of charges. That is what is the conducting nature, hence the name conductor. Insulator, it doesn't show the character of allowing the flow of charges, and that is why it is called as an insulator, the dielectric. Now, this is about modern theory of electron. Now, let us come to the other properties like additive property of charge. In fact, I should have told you this property earlier. Sequence has missed, sorry for that. This is additive property of charge. What is additive property? We said charge is a scalar quantity. In physics, whenever we are talking about physical quantities, how to find the net or resultant? If it is scalar, there is algebraic addition that we follow. If it is vector quantities, then we have to follow the special laws of addition such as triangular laws, parallelogram laws, the polygon laws. Now, since charge is a scalar, we use algebraic addition. What is meant by algebraic addition? Yes, though you know, one more time, see here. Suppose I have a system. I have a system in which there are Q1 amount of positive charge, Q2 amount of negative charge. It has both positive and as well as negative suppose. Or the total positive charge in the system is, I have taken as Q1, and the total negative charge in the system is Q2. Earlier we have discussed the case of atom. Negatively charged electrons and positively charged protons. If we consider atom as a system. Likewise, if a system has this total negative charge and positive charge, then the net charge is always given by this plus Q1 minus Q2. See here the sign is very important. All the positive charge we are taking, and when we are taking the net charge, whatever sign is there for the sign, along with the sign we have to use. How? One more example you see. Supposing this is a copper sphere. This is a copper sphere with a positive charge of 3 microcoulomb. Now, if added with the it has initially 3 microcoulomb. Suppose now it is said that a excess of minus 2 microcoulomb is added. What will be the charge here? Right? So initially what is Q1? Q1 is equal to 3 microcoulomb, and what is Q2? Minus 2 microcoulomb. It is added to this only charged one. Therefore now what will be the net charge or the final charge is, this is plus 3 and this is added is minus 2, that is equal to plus 1 microcoulomb. Suppose if you are adding minus 3 microcoulomb to the already existing 3 microcoulomb, then this plus 3 minus 3 becomes 0, neutralizing the charge. So whenever we have to add the charge, the addition of the charge is, because of the scalar nature, use the sign that is given to the charge. So this is what is additive property of charge. Now comes very important property number 4. This property number 4, again I am writing it as a 5-star property, 5-star characteristic. What is that? Conservation of charge. See, in physics we come across so many principles of conservation. In first PU also you have come across conservation of mass, conservation of momentum, conservation of energy, conservation of angular momentum. Remember? Similarly here it is conservation of charge. Generally, whenever somebody asks you a conservation law, what is that conservation of energy? Your immediate answer is energy is neither be created nor be destroyed. You give such statements, right? At least at the PU level, let us not use such statements. Let us use our statements with better understanding. Here also sometimes what is conservation of charge? Charge can neither be created nor be destroyed. Yes, we can give that statement, no issues, but it doesn't carry a good meaning. Therefore, conservation of charge, I will make it as 1 or 2 or 3 statements. Let us at least make it as 2 statements. What is that? Total charge, which we call net charge. Remember, any of these terminology can be used. The total charge or net charge of an isolated system. Isolated system. Don't forget this isolated. An isolated system. Now you may get it down. What is meant by a system, or how it is different from isolated system? Yes, let us explain. Just first you watch this English part, then we will come to the physics part. The total, that is net charge of an isolated system, always remains constant. Always remains constant. That is both in terms of magnitude and also sign. Sign is important. When we say total charge of the system, it can be either 0 or it can be positive or it can be negative also. So the conservation is not just with respect to the number, that is magnitude, but also with respect to sign. Now let us see what is meant by isolated system. Supposing I take a system. Here, supposing this is some system, you say atom or any other thing. This is system A, and in its neighborhood there is one more system also. I will consider this system as B, such that there is an interaction between A and B. Right? There is an interaction between A and B. Then, what is meant by system and isolated system? See here. Supposing here, now I consider the system A alone, it cannot be an isolated system. Why? Because it is interacting with this system B. Therefore, A alone, we cannot treat it as an isolated system. So here, that isolation refers to the absence of any interaction. No interaction should be there. Then it is what is isolation. Right? Now that in the days of Corona, this isolation is a very familiar term and we all understand. A person with Corona positive is took to isolation. He is not allowed to interact with any other person. Right? So that is what is the meaning of here isolated system. So A is a isolated system only when if it is not interacting. Now supposing if I consider both A and B as interacting systems, A and B both I will consider, but these both taken together we call it as a system. Now that system has both A and B. Now we can consider this as a system also. Both A and B are now systems. Such that, supposing what is the total charge of the system A? Total charge of the system A, supposing what it is 4 microcoulomb positive charge, and B has a total charge of minus 1 microcoulomb. Then what is the meaning of this conservation? Now, we said that, now let us give one more better example for this. One more better example to understand conservation, and this is also an important thing in our numericals as well. Supposing let us take, this is a copper sphere radius capital R, I name it as some A, sphere A, with a charge of plus 4 microcoulomb. Now this is another sphere, copper sphere. Let me take it as same radius, same size, both have same size. This is another copper sphere B, and it has a charge supposing of minus 1 microcoulomb. Now, when we consider these two systems, what is Q net? Because now A and B are taken as one system. Q net is equal to plus 4 minus 1, that is equal to plus 3 micro, submultiple is there, plus 3 microcoulomb positive of, so this is what is the net charge. Now let us suppose that these two spheres are made to touch with each other. How is that? It is not by casual methods. Using some insulating materials, we allow A and B to touch each other. Suppose A and B are touched with each other, what happens? They start interacting with each other. Such that, earlier we have told, any interaction, one in the system, if one loses electrons, the other will gain electrons. On that principle, now, this is all the case before touching. Shall I say? This is the case before touching. Now, after touching, I am writing. After touching. Please do remember we have taken the case of two spheres of equal size. Both are conducting spheres of same size. Underline this point over another time and again. Supposing if it is a different sphere, different sizes, what happens will be an interesting thing which we will do in the latter part of our discussions. Right? Now we are talking about same size. Now after touching, what happens? Initially QA was plus 4 microcoulomb and QB is equal to minus 1 microcoulomb. Now after touching, yes, this is before touching, and now after touching, what happens? The charge redistribution will take place. The same charge or unequal charge, same size or unequal size, what happens? Yes, redistribution of charge. Follow the term I call it redistribution of charge. Same size or different size, but now we are taking the case of same size. I am repeating this time and again. Do remember, because afterwards different size, we should not use the same principle, and that is why I am telling you time and again. Now after touching, what happens? This QA dash is equal to QB dash. I am using price. QA and QB before touching. After touching, QA becomes QA dash. QB becomes QB dash, such that QA dash is equal to QB dash is equal to QA plus QB by 2. Now they distribute charge equally between them. This equal distribution is the case when same size arises, but not the other times. Therefore now QA plus QB by Q2. by 2. So what is the answer here? It will be plus 4 minus 1 by 2, that is equal to, yes, plus 2 plus 3 by 2 microcoulomb on each other, on both A and also on B. Now you see, before touching, what is the net? What is the net? Plus 4 minus 1, it is plus 3 microcoulomb. Now after touching, what is the total charge? Now the numbers are plus 4 and minus 1. Numbers are changed, you will see. Plus 3 by 2 microcoulomb. The other one is also plus 3 by 2 microcoulomb. Is it not? Numbers have changed. But what is not changed is this number. Plus 3 microcoulomb. Here also, what is the total charge after touching? It is plus 3 microcoulomb only. That is, the net charge is remaining the same. Individual charges may be changing in the interaction between them, but the total charge remains the same, is the principle or the consequence of conservation of charge. Therefore, now that statement, charges neither be created nor be destroyed, actually the numbers are changing. So the charges magnitudes are changing, and that is why I asked you not to write that statement, charges neither be created nor be destroyed. May be true in one sense, but this is the best representation of the principle that the total charge of an isolated system always remains constant. When I have given, let me write an expression also for this. What is that? The total positive charge in the system. Let me take Q plus Q minus the total positive charge in the system, the total negative charge in the system. When we have taken that resultant, if we do it as a capital Q, that is equal to constant. This is a conservation of charge. We have both quantization of charge and conservation of charge, a very unique case in physics. In all other parts we have quantization separately followed by some and conservation followed by some, but both conservation and quantization holds good for charge. Now, having said this, let us add one more important thing. You write it with underlining in your notebook, that as earlier I have told you, there are many laws of conservation principles in physics. Conservation of mass, conservation of energy, conservation of momentums, linear momentum and angular momentum, conservation of charge, now that we have told. In all such cases, conservation of mass, conservation of energy has some exceptions. Conservation of mass is violated in some cases. Conservation of energy is violated in some cases. Like we take the case of popular nuclear reactions. In the nuclear reactions, mass alone is not conserved. Energy alone is not conserved. There what is conserved is mass plus energy is conserved. So in such case, conservation of mass has exception, is a true statement. That is, it violates at some cases. Answer is yes, it is a true statement. Similarly, conservation of energy has exception. The statement is true because, example, the case of nuclear reaction. Energy neither be created nor be destroyed. That is why we should not use that statement while writing a statement of the conservation principle. Whereas, conservation of charge has no exceptions in the nature. Whether it is microscopic interactions, macroscopic interactions, physical interactions, chemical interactions, biological interactions, whatever you call, conservation of charge has no exception. It is a law of nature without any exceptions. Similarly, the conservation of linear momentum, right? We have taught in the first PU. That is also a universal law without any exception. So till now we have covered three characteristics of the charge. Number one, the quantization of the charge. Number 2, additive property of the charge. And number 3, the conservation of charge. Now let us see 2 more very important and very interesting characteristics of charge. I said interesting property. How interesting it is, you see. The character is the expression of charge, spelling E-X-P-U-L-S-I-O-N, expression. When we say expel in English, it is E-X-P-E-L. Remember? Now what is this expression of charge? And its character is applicable only for conductors, not for insulators. Suppose now I take a conductor of any shape. Any shape I am telling you. Here I may show sometimes sphere or most of the time sphere or sometimes other shapes. But it is applicable for any shape. So conductor is charged. Earlier we have told according to electronic theory what is meant by conductor is charged. Either loss of electrons, therefore it will acquire net positive charge. That net positive charge is what is called as excess charge. Similarly, gain of electrons, it will have net negative charge, and that is what is called as excess charge. So conductor, when it is charged, it acquires excess charge, excess positive or excess negative charge, such that, look at the property of a conductor. Supposing I have a conductor in the form of a sphere, a conducting sphere I have taken. If this sphere is charged, it acquires that excess charge, such that the conductor shows a property that it just makes all the charges, it pushes all the charges onto the surface. Supposing if I take the case of excess positive charge, all this charge will be pushed onto the surface. But why this pushing, why this character? We will understand in the latter part of our electrostatics. Till there is a lot of time for that. When we reach that time, one more time I remind you there, this is what is the property, and that is why the expression of the charge also. Supposing even if it is, supposing if I take some arbitrary shape, let me take, suppose if I take an object like this in this form, irregular surface, and suppose now here I have given excess negative charge, and all the charge will be distributed only on the surface. That is what is the property of expression of charge. When a conductor is charged, all the excess charge will be pushed onto the surface, such that inside the conductor net charge is 0, is the statement. You write that in this statement, conductor when charged, the excess charge will be expelled, E-X-P-E-L-L-E-D, expelled onto the surface such that inside the conductor net charge is 0. Now supposing if I call this some inside point, Q, I for inside is 0, and all the charge will be only on the surface, is what is the property. Now remember, because of this property of expulsion of charge, whenever we come across the cases of a charged conductor, the distribution is only surface distribution but not volume distribution. Suppose inside the conductor also, this is not the hollow sphere I have taken, this is a sphere I said, with all material stuff inside. If supposing charge is distributed inside also, then we call it as volume distribution. Now in the case of conductor, volume distribution of charge never possible. It never happens. Only surface charge distribution will happen. So volume distribution of charge is possible only with insulators, which does not exhibit the property of expulsion of charge. So two takes that we take from this character is that for any conductor when charged, we only get surface charge distribution but not volume distribution. Second property, second take that we can take from this character is that in the case of insulator only in the case of insulator we can have the case of volume distribution of charge. And also now here you see, because charge is entirely residing on the surface, now we define one important parameter. In this particular chapter, it's a very important parameter we use quite frequently. That is surface charge density. Surface charge density, a new parameter. Symbol sigma. Symbol is sigma. Electrostatics sigma. Because different units, same symbol will have different meaning. We are now telling with respect to electrostatics. Symbol sigma as sigma is equal to charge on the conductor. Whenever we say charge on the conductor, of course the excess charge by surface area. Let me write charge by surface area, because whenever it is area, it can be either area of cross section or surface area. This time it is, yes, charge upon surface area is sigma. What will be the SI unit? Yes, this is what I have told you in the very beginning. Now you know the unit of charge. Our first session we have told charge SI unit is Coulomb, and area, since you are high school you are using it. Therefore use that known to unknown. So what will be SI unit? It is Coulomb. If you are writing Coulomb, C-O-U-L, C small, by meter square. That is what I write, C by meter square. The SI unit. Now you will find that the sigma and surface area, they are inversely related. We have good implications, or we have good examples to understand the principle or to find the application of such case. Sigma proportional to 1 by area. Can we use it anywhere, or where do we use it with such principles? We'll continue our class tomorrow. Till then, 2 sessions have happened. Please make a small notes of your understanding. Revise it once or twice. Any of your doubts, contact your teacher. Have a very, very good day. Thank you.